Okay, this is a short video to finish up Chapter 5. The topic is distribution functions, which really basically is another name for a histogram. At least a histogram is a type of graph that shows the distribution function. Here's an example of one. What someone has done has been to take all of the writings of Shakespeare, enter them in a computer somehow, and then have the computer go through and count the lengths of the letters, the lengths of the words, the number of letters. So some words have one letter, some have two, some have three, some have four. A few words have as many as 10, 11, or 12 letters in them. And this graph shows the relative counts. Over here on the vertical axis, notice that it is percentage. And so apparently in Shakespeare's compiled writings, about, it looks like 5% of the words that he used overall were one-letter words, and about 17 or 18% were two-letter words, and 22% or so were three-letter words, and so on. Just as an aside, why would you want to do something like this? Linguists are people who study styles of writing, and one of the jobs they have is occasionally trying to determine authorship of an unknown work. So even today, now, occasionally somebody stumbles across an old manuscript in an attic somewhere in England, and it's a play, and it looks similar to some things that Shakespeare perhaps wrote, or that Shakespeare did write. And so the question is this play that doesn't have a name on it really one of Shakespeare's, or did somebody else write it? Well, it's impossible to know for sure, but one way of trying to decide which way you would lean would be to do a word count of the new play that was found and make a distribution function for that play and then compare it to Shakespeare's distribution pictured here. The idea is that we tend to maintain a similar writing style. So if Shakespeare was using lots of 2, 3, 4, 5-letter words in various proportions in his known writings, and the play that we found has a very different distribution, that person, say, was using a lot of 6, 7, 8, 9 letter words, then you would tend to think, okay, this somehow, the writing style seems to be different than Shakespeare's. This person is using more larger words than Shakespeare tended to use. And so you'd say, well, probably this wasn't Shakespeare. But if the word length distribution in the unknown play looked very similar to this one, then that would be some evidence, not proof, but some evidence that perhaps Shakespeare wrote the play that you just found. So that's an example of why you would want to make a distribution function. Just a quick question, what's the total area of all the bars in the following histogram? So notice that the rectangles here are each 1 unit wide, and so the area is height times width. The width is 1, and so the area is just the same number as the height. Question, what do all of these areas have to add up to? Well, every word has to be 1, 2, 3, 4, or some number of letters, and there's a 100% chance of something happening, a 100% chance of a word having a certain number of letters. So all of these have to add up to area 1, or 100%. Tuck that in the back of your mind, and we'll use that fact in just a moment. The most important distribution function by far is what's called the normal distribution, which is just another name for a bell curve, which I'm sure you've seen before. Many biological measurements follow a bell curve or normal distribution. So for example, the height of U.S. adult males follow a normal distribution with mean about 69 inches and standard deviation about 2.8 inches. Here's the notation that we'll use, normal, and then first you give the mean, so this number is x bar, and second you give the standard deviation, so this number is s. Alright, so let's take information about x bar and s and see if we can draw the graph. The answer is yes, you definitely can. If you know x bar and you're interested in drawing the distribution, This shape, by the way, could be the envelope of a histogram like we talked about in the lecture before last. What you do is draw a bell curve and make sure that its peak is at the mean. And now, regarding the role of the standard deviation, let's come out here and notice that in this region the shape of the curve is curved downward. The curvature, if you're going to curl your hand around the curve on this part, you need to put your palm down. So that's mathematically called concave down. Whereas out here, the curvature is in the upward direction. If you're going to curl your palm around the curve at this point, you need to hold your palm up. And so this is concave up. And somewhere in between, about right here, is a place where the graph switches from concave down to concave up. Likewise, on the other side, there's a place about right here where the same thing happens. Out in here to the left of that point, you're concave up, then you're concave down along here, and then concave up again here. And so if we keep track of those distances, the point of all of this is that this distance right here is S. And the picture is symmetric, so this distance to the other side from the mean is also S. Okay, so those two numbers, the mean and the standard deviation, completely determine which bell curve you're talking about, because actually there are an infinite number of bell curves at different positions and with different shapes. The mean turns out to control the position. If I change the mean, this curve just slides back and forth with its peak at a different place. And the standard deviation controls the shape, or the spread. Because some bell curves are skinnier than others. If the standard deviation is large, then the bell curve is going to be spread out. If it's small, then it's going to be thinner. Let's go ahead and sketch normal curves or bell curves with these means and standard deviations. First of all, with mean 5 and standard deviation 1. Here's 5, so that's going to be the peak of the bell curve, and then standard deviation 1 means we have to go out 1 unit before we change from concave down to concave up. So this type of shape out both directions, and then I'll finish it off like this. By the way, the tails of the bell curve never end. They just keep coming down, 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 and getting closer and closer, but never touching the x-axis. So eventually we just have to, on a piece of paper, we just have to stop drawing. But it's important to keep in mind that this goes on forever to the right and to the left. And so this is the graph for A. For B, normal curve with mean 2 and standard deviation 1. Remember, the mean controls the position, so we've changed the peak from 5 down to 2, and other than that, the shape and the rest of the curve stays exactly the same. So a curve something like this, and this is B. And then 3, mean 2 and standard deviation 3. So the peak is at 2, but now the standard deviation is 3, and so the change in concavity from concave down to concave up doesn't happen until way out at 5, and then in the other direction down 3 takes me back to -1. So this curve is going to be a lot more spread out. Now let's go back and refer to this comment. The total area of all of the bars in a histogram has to be 1, or same thing, the total area underneath the distribution curve, like this one, has to be 1. And so if I'm going to now draw a curve that's in the same position as the green curve, but is more spread out, and still only has total area 1, just like the green curve, the curve also has to get shorter. If I'm going to spread it out more, then the height has to come down to keep the total area the same. And so it's a curve that's shorter here, and now it's going to go out to 5 before changing concavity, and back to -1 before changing concavity. So this is curve C. So if I know the mean and standard deviation, I can draw the appropriate bell curve. That's used in probability a lot, but let's just do a couple of calculations with something related to it. It turns out that because a bell curve is a definite shape, if you know the mean and the standard deviation, you can talk about what percentages of data have to be within certain distances from the mean. And so something called the empirical rule specifically talks about how much data, what percent of the data needs to be within 1, 2, and 3 standard deviations of the mean. Let's look at this picture. I'm drawing a situation where the mean of the curve is 0 and the standard deviation of the curve is 1. But this works for any bell curve. So here's the mean at 0. If I go out 1 standard deviation from the mean in both to the right and to the left, I'm going to pick up 68% of the data. It just has to be. The curve is tallest near the mean, and so most of the data is going to be concentrated in a region not too far away from the mean. Specifically, 68% of the data within 1 standard deviation of the mean. If I go 2 standard deviations from the mean, then I pick up 95% of the data. Of course, if I go farther out, then I'm going to get more of the data. So between the numbers -2 and +2 on this graph, 95% of the area is included. And if I go out 3 standard deviations from the mean, now I'm getting 99.7% of the data. This is very powerful if you think about it. Pick any data set that you like and draw the distribution. If it turns out that that distribution is bell curve shape, then within 3 standard deviations of the mean, essentially all of the data is located. There can be just a trace of outliers at the high and low ends, but basically all of the data in a normal distribution is within 3 standard deviations of the mean. Let's use that principle to do some problems. Example, I'll just read it here. Suppose the mean GPA of students at a university is normally distributed with mean 2.4 and standard deviation 0.75. The university wants to recognize the top 2.5% of its students by grade as graduating with highest honors. What's the minimum GPA for a student to be able to graduate with highest honors? Okay, first of all, the grades were said to be normally distributed. So let's just start out by drawing ourselves a bell curve. And on this axis is GPA. And the peak is about here. All right, we know from what we talked about on the previous page that the mean is occurring here. And I'm interested in discussing the top 2.5% of the students, or of the GPAs. So down here are the lower GPAs. Here are the roughly average GPAs, and the highest GPAs are up here in the right tail, it's called. So what I would really like to do is find a GPA for which 2.5% of the data lies above. So here are 2.5% of the students with the highest GPAs. These are the ones that are going to graduate then with honors by this university's criteria. Okay, let's then start thinking it through as follows. The picture is symmetric across the mean. And so if there's a highest 2.5% of the data, there's also correspondingly a lowest 2.5% of the data. The same distance away from the mean down below as this one was up above. So I'm not really interested in discussing this 2.5%, but I know it's there. And now let's use the principle that there is 100% of the data underneath the entire curve. So if 2.5% of the data is in the low tail and 2.5% in the high tail, that's 5% altogether of the data that's in the tails, and that leaves then 100% total minus 5% in the tails, or in other words 95% of the data in the middle regions here. So between the two red vertical lines that I drew, 95% of the GPAs are going to fall. Okay, that number rings a bell. We've just talked about a picture like this that says 95% of the data lies within 2 standard deviations from the mean. And so that tells me that this number, this distance, is going to be 2 standard deviations from the mean. I'll write that as 2 times s. So s is a particular number. I actually know what it is, but to illustrate the technique here, I'm just going to write this distance as 2s, and then of course this is the same distance going the other direction, 2s. So in particular, this now started at x, and then I went up or added 2s, and so this number is x bar plus 2s, and this number is x bar minus 2s. The one I'm interested in is up here at the top. I have to go 2 standard deviations away from the mean to get the 95% of the data in the middle, and then what is that number? Well, the mean here is 2.4 plus 2 times, and the standard deviation is 0.75. And so the answer to the question then, when you crank this number, is 3.9. That's a high GPA, but we're talking about graduating with highest honors, and this is a fairly stingy university. It's only going to give that distinction to 2.5% of the students. So this is close to a 4.0. Let's work one more example. You might want to pause the video and try to work it out on your own. Suppose the lifetime of a brand of car battery is normally distributed, that's the bell curve shape again, with mean 45 months and standard deviation 8 months. What's the longest warranty the manufacturer can offer without replacing for free more than 16% of all batteries sold? Okay, lifetimes are normally distributed, so it's a bell curve situation again. On this axis, we're graphing lifetime in months. And like all bell curves, the peak is at the mean. Okay, a number, a percentage, 16% is specified. And we don't want more than 16% of the batteries to have to be replaced for free. So the way a warranty works is that a certain number of months in this case are specified, and then if your battery fails before the warranty period is up, you take it in and the manufacturer gives you a new battery for free. If your battery fails after the warranty period is up, then it's your responsibility. The manufacturer doesn't replace it for free. You have to pay for another one. And of course, the manufacturer doesn't want to have to replace very many of the batteries for free. That's giving away product that he's not making money on. So 16% is a relatively small number. You would never want a situation where you were going to replace like 95% of the batteries for free or something like that. And specifically, which batteries get replaced for free? Those that fail at a short lifetime, or an average lifetime, or a long lifetime? A short lifetime. Those that don't last very long, that have a short lifetime, are the ones the manufacturer has to replace for free. So somewhere out here, I'm looking for a warranty period that I'll set for which only 16% of the lifetimes are less than that number. And now let's play the same kind of game that we did before. If there's a lowest 16%, then there's a highest 16%. And 16 plus 16 is 32, and 100 minus 32 is 68. So here in the middle is 68% of the battery lives. But I recognize that number too. From the empirical rule picture again, 68% of the data lies within 1 standard deviation of the mean. So in my picture, I need to go out 1 standard deviation, or 1 times the standard deviation, to the right and to the left in order to pick up 68% of the data. And as we said, this is the number that we're interested in. From the picture now, it's x bar minus, because we're going down to the left, minus s. So the answer to the question is x bar minus s. The warranty is x bar minus s, which for the numbers given is 45 minus 8 equals 37 months. If that's where I set my warranty period, and the battery life distribution really is as stated here, then I'll end up replacing about 16% of the batteries for free, and the other 84% of the batteries will fail after the warranty period, and the customer will have to replace those. Thank you.